Hello dear students, I welcome you back for lecture number 3 on the topic electric potential and capacitance. So in previous class we were able to understand electric potential due to dipole. So today we are going to determine the potential energy due to system of two charged particles in the absence of electric field. Now as you remember, electric potential is nothing but the amount of work done by unit positive test charge from bringing that point from infinity to the point against the direction of the electric field. So today we are going to find the potential energy for system of two charged particles in the absence of electric field. Now students, consider I have two charged particles Q1 and another charged particle Q2. They are separated by certain distance R. Okay, let this be at point A and this be at point B. Now students, I have a system of two charged particles. I have a system of two charged particles, and these two charged particles will possess certain potential energy between them. And this potential energy I am going to determine in the absence of electric field. Now students, just try to understand this situation. I have one charged particle Q1, and this charged particle is brought from infinity to the point E, right? Then this charged particle has done certain amount of work, right? Let that work be W1. Okay, and one more charged particle plus Q2 is brought from infinity to the point B, okay, and let this charged particle has done work W2. So what will I get? I will add these two works, W1 plus W2, so that I'll get net work, that is W. So amount of work done is nothing but the potential energy possessed by these two charged particles. So have you understood the consideration what we are doing? Yes. So students, one by one will find the work done by the charged particle Q1 and work done by the charged particle Q2. Then I will add up and I will get the total work done. And once I get the total work done, I am going to get the potential energy possessed by those two charged particles. So let W1 be the work done by charged particle Q1. Let W1 be the work done by the charged particle Q1. Now Q1 is brought from infinity to the point A. Q1 is brought from infinity to the point A. Now students, here there was one condition. We are going to find potential energy in the absence of electric field. So since there was no electric field, so what amount of work is done by the Q1? Obviously it will be 0. Yes or no students? Because electric field is 0 and work is done against the direction of the electric field, which is 0 itself. So work done by this charged particle will be 0 because there is no force exerted on this charged particle. Understand students? I have brought Q1 from infinity to point A, and that now whatever work I have done in the absence of electric field. There was no electric field. So if there is no electric field at point A, it has experienced no force, and once the charged particle has experienced no force, work done will be 0. Yes or no? Because work done, what it tells, force into displacement. Are you understanding? So W1 will be 0. Let W2 be the work done by Q2 from bringing that point charged particle from Q2 to the point B. So already there was Q1 here at point A. Now you are bringing one more charged particle Q2 from infinity to point B. Now again students, there was no external electric field, but you know that initially this Q1 charged particle was already existed here. Now this charged particle would definitely have certain magnitude, right? Yes or no students? As a result, it will generate this space around it, and this space is nothing but the electric field, and this electric field will be obviously radially outward since it is the positively charged particle, and this electric field will exert force on this charged particle Q2. As a result, this charged particle has to do the work against the direction of the electric field. Yes or no students? Clear? Are you understanding? So this charged particle is doing certain amount of work against the direction of the electric field. So let W2 be the work done by the charged particle in bringing the charged particle to the point B. So W2 will be nothing but what? What will be W2? You know that potential V is nothing but work done by unit charge or the test charge. Potential is nothing but work done by test charge. So from this, work done will be what? Potential into charge, right? Yes or no, students? Right. So what is work done here? Potential at point B, potential at point B. This potential at point B is due to Q1 into the charge, which is the charge particle V2. Yes or no, students? See here, again try to imagine A. At A I have Q1 and at B I have Q2. This charge particle has done no work because there was no external electric field. Definitely again there is no external electric field when this charge particle is trying to encroach this space. But this charge particle now acts as a source charge, and this source charge will generate the electric field radially outwards. As a result, this charge particle will experience electrostatic force of repulsion. As a result, this charge particle will be doing the work against the direction of the electric field, right? What will be that work? Work done will be by this charge particle will be W, that is potential at point B due to Q1. The potential at this point is because of this charge particle Q1 into V2, because you know that again potential is work done by the charge particle. So potential work done will be what? Potential into Q. So potential at point B due to Q1 will be what? 1 upon 4 pi epsilon naught Q1 by. So W2 will be 1 upon 4 pi epsilon naught Q1 by R. Yes or no? Into Q2. Yes or no? Into Q2. Yes or no, students? Correct. Sorry. Potential, this will be potential at point B due to Q1 will be V1 into Q. Are you understanding? Into Q2. Clear? See here, students, don't get confused here. Listen there. W2 is work done by the charge particle, second charge particle, from bringing that point at point B due to Q1. Okay, so Q1 has potential V1, that potential is V1, and who is performing the charge work done by the second charge particle. Therefore W2 will be what? W2 will be V1 into Q2. So V1 is 1 upon 4 pi epsilon naught Q1 by R into Q2. Clear? So students, total work done W will be W1 plus W2. Yes or no? So W will be 1, this will be 0. W2 is 1 upon 4 pi epsilon naught Q1 Q2 divided by R. Now this work done is stored as potential energy. As per from work energy theorem, what it tells you? Work done is equal to change in the energy of the body. So this work done is stored as potential energy, which is denoted by U, that is 1 upon 4 pi epsilon naught Q1 Q2 divided by R. Clear, students? Are you understanding? See here, very simple derivation, and it's not that much complicated also, but try to visualize the thing. We have two charge particles Q1 and Q2. Q1 is placed at point A. So initially Q1 will be performing the work W1. That W1 will be 0 because work is done in the absence of electric field. There was no electric field. Thus charge particle is performing work that point from infinity to the point A. Therefore W1 will be 0. W2 will be doing the work. Why? Because initially there was no external electric field. But once the charge particle Q1 came there, he will exert the electrostatic force of repulsion on that charge particle Q2. As a result, Q2 should do the work. How much work Q2 should be done? Potential at point B due to Q1 and into charge Q2. So what will be the work done? V1 into Q2. So V1 is what? Potential of the charge particle at point A, that is 1 upon 4 pi epsilon naught Q1 by R into Q2. So total work will be W1 plus W2. So W1 is 0, W2 is this. So net work will be 1 upon 4 pi epsilon naught Q1 Q2 R. So this work done is stored as potential energy. Clear, students? Are you understanding? Okay. So one of the easiest derivation, but similarly you can also find the potential energy for n number of charges, 3 charges, 4 charges, or infinite amount of charges. Okay, now students will be doing one more important derivation. Okay, we'll be doing one more important derivation, that is relation between electric potential and electric field or electric field intensity, I would say, or show that E is equal to dV by dx. Students, now already you know that what is the relation between electric field and electric potential. Already we know that electric field is given by 1 upon 4 pi epsilon naught q1 q2 divided by r square. This is E, and V is given by 1 upon 4 pi epsilon naught q1 q2 divided by r. From this equation we can see that E is equal to V, but only thing is I have r square and here and I have r here, so E will be equals to V by D. Okay, so same relation we are going to derive it by taking help of differentiation and little bit of the potential energy also. So students, what they are asking is, they are asking the relation between electric potential and electric field intensity, or else directly they may ask you in the exam that show that E is equal to minus dV by dx. So this is the expected equation that we want to derive it. Okay, so we'll begin this derivation. Now student, consider I have one charge particle q1 placed at point P. Okay, now this charge particle will give the electric field radially outward, since it is a positively charged particle. So electric field will be radially outward. Now consider I have one test charge q0 at point A, which has a magnitude of 1 coulomb. Okay, now see here students, this test charge is having very less magnitude compared to this source charge. So you know that as a result it has to do lot of work in order to approach this space q1. So what happens, I have a source charge and at point A I have one test charge which has a magnitude of 1 coulomb. The direction of electric field is radially outwards towards the point A. Now consider this charge particle or this test charge particle is doing certain amount of work and it approaches this point B. So definitely it has done certain amount of work, and this work done will be stored as its potential energy, right? So if imagine at this point if I have potential V, so what will be the potential at this point? Definitely it will be V plus dV. Yes or no students? Correct. Are you understanding? You know that as the charge particle is going towards the point q1, the potential will increase. Yes or no? If the potential at this point is 10 volts, so at this point it may be 20 volts, 30 volts, 40 volts, 50 volts. As I go towards the source charge particle, the potential will go on increasing. So at this point it has the potential V, so it has done certain amount of work and its potential has increased from V plus dV. Okay, so if this is the distance x from source charge particle to the point A, so it has undergone certain displacement, that displacement be dx. Are you understanding? So now we will find the relation between this electric field intensity and this potential. Are you understanding? Have you understood the diagram? It's quite simple. I have a source charge particle, I have one test charge particle which has magnitude of 1 coulomb placed at point A. As a result, Q0 is doing certain amount of work against the direction of electric field. As a result, its potential will increase from V plus dV. So as you remember, there is potential difference created here. Yes or no students? And that potential difference is nothing but the work done. So remember this logic and we'll straight away begin with the derivation. Now students, you know that potential difference, already I told you, potential difference is amount of work done between any two points. Yes or no? Potential difference is nothing but the work done. Yes or no students? So whatever is the potential, that much will be the work done. Now you know that potential difference will be always VB, greater value minus smaller value. So potential at point B will be maximum compared to the point A. So potential at VB, that is V, potential at VB was V plus dV. Yes or no? Minus potential at V was minus V. It was V and this minus sign. Potential difference. Yes or no, student? So potential difference V is equal to potential at point B, that is V plus dV minus V. So this V will be equals to minus V plus V gets cancelled. So potential difference will be what? dV. Potential difference will be dV. Yes or no, students? Correct. So you know that again work done is equal to dV. Potential difference is amount of the work done. So how much is the potential difference? It is the dV. Now you know that potential difference is force into displacement. How much did the charge particle undergo displacement? Minus dx. Minus dx indicates that displacement has decreased or the work is done against the direction of the electric field. So this will be dV. Correct. Now what is this force? This force is the electric force, and you know that electric field is given by, I'll write it here. Electric field is nothing but force experienced by the test charge. Yes or no? So Q naught is 1 coulomb. Therefore E becomes equal to F. Correct? Right? So instead of writing F, shall I write E, because the equation demands electric field. So E equals to minus dx equals to dV. Correct? Are you understanding? Therefore electric field intensity will be dV by dx, minus dx. So here negative sign indicates, what does it indicate? Negative sign indicates work is done against the direction of electric field. Work is done against the direction of the electric field. Are you understanding, students? So very simple derivation. Just you have to remember the certain definition that potential difference is the difference at two different points. So I had two different points, that was VB and VA. So at VB the potential was V plus dV, and at VA it was V. So V equals to dV. So work done is equal to this much potential difference. Work done is force into displacement. Force is what? E is equal to F from this equation. So E equals to dV by dx. Are you understanding, students? Okay. So certain things you have to remember here. If potential is constant, imagine if V, this V is constant, so electric field will be 0 or electric field intensity will be 0, because if it is constant and differentiation of constant will be 0. Okay. So if it is constant then it will be 0. Clear? Have you understood this derivation? Okay. Now few things you have to remember. What is the work done by the charge particle revolving once around the circuit having radius, certain radius r? So work done by that charge particle. See here, students, if I have one charge particle Q naught and at center I have source charge particle, they have radius r, and this charge particle is revolving around this source charge particle. What is the work done by the Q naught? It will be definitely 0. Certain terminology you have to remember. Clear? Okay. Now, what will be the potential energy and kinetic energy of electron moving in the direction of the electric field? That you have to remember. Now, the question is, what will be the potential energy and kinetic energy of electron and proton moving in the direction of the electric field, towards electric field? Come on, tell me. Come on, tell me. See a student, I have a proton. If you remember, proton is a positively charged particle. Now this proton is doing certain amount of work, and this amount of work is along the direction of the electric field. So if the proton is positively charged particle, electric field will be again radially outwards for charge particle Q, because both are this, towards the direction of the electric field. As a result, what will happen? Its kinetic energy will increase. Its kinetic energy will increase, and if kinetic energy increases, its potential energy decreases, because as per law of conservation of energy, if kinetic energy should increase, then potential will decrease, so that the net energy of the system remains constant as per law of conservation of energy. if I have the electron, which is negatively charged particle, now the direction of the electric field is radially outwards, and you know that electron is a negatively charged particle. As a result, it will be attracted oppositely towards the direction of the electric field. So what will happen? Its potential energy will increase and its kinetic energy will decrease. Clear? Are you understanding? Okay. One more thing, conditions for the electric field to be 0. Now, if I have a charged sphere, uniformly charged sphere, now you know that charge will be distributed on the surface of the conductor, right? On the surface of the conductor, right? Since the first class only we are studying this. So, electric field inside the conductor will be 0. Are you understanding? But at this point, electric potential will not be equal to 0. Take care of this, because if a charged particle is placed here, in order to approach this space, this has to do certain amount of work. Are you understanding? So, though inside the charged sphere electric field will be 0, but not necessarily potential should be 0. Clear? Are you understanding, students? Okay. And potential, it will be 0. Potential energy will be 0 between midpoint of two unlike charged particles separated by certain distance but having same magnitude. So these all conditions you have to remember. When potential will be 0, where it will be 0, where it will be maximum, when the kinetic energy will be maximum. So potential at midpoint will be 0 for two unequal oppositely charged particles which has same magnitude separated by distance, but they will have certain electric field. So these are the few things that you have to remember. Also you should know that if I have plus Q and minus Q, then electric field inside this will be of certain magnitude, but outside it will be 0. Outside this sphere it will be 0, because plus will be getting attracted towards the minus and this will be radially outward. So if I have same charge particle plus Q and plus Q, then electric field will be inside it will be 0 and outside it will be having certain magnitude. Clear? Are you understanding? So for this, outside it will be 0 and inside E will be something, will be having certain magnitude. So these all conditions you have to remember, because you know that plus minus they will be attracting radially inwards. There will be attraction. As a result, attraction, the electric field direction will be inside. So inside this magnitude there will be certain electric field, outside it will be 0. For plus plus or minus minus, electric field will be radially outwards. So electric field inside will be 0, but here there will be certain electric field. Have you understood this? Oh. So we'll meet in the next class. Okay, I hope you have followed whatever I am teaching. Okay, thank you.